Thank you very much, Catriona. Good morning, all. I guess for most of us it is good morning, not for all, I realize. I'm really delighted to be here and talk a bit about the challenges of modeling the coupled Earth system. So the main motivation, as I will explain you in a minute, is climate change, of course. But to model climate change and future climate change, we have to understand the coupled system of the Earth. And that's just the first thing I want you to realize. When we talk about climate change, we think of, changes in weather, in precipitation, temperature, and so on. So things related to the atmosphere. But it's really governed by this interplay of all the systems of the parts of the Earth, of the atmosphere, the oceans, the land surface, and so on, the biosphere, most obviously. And it's, all these interactions we, in essence, have to take into account in our models of the Earth system to get things right and get to reliable projections for future climate, for example. So by no means try to read and understand what's in that graph. That's just to show you, probably just a selection of all the processes and interactions going on the atmospheric side of things, interactions with the oceans, with the land surface, and so on, and including physics, including chemistry, and this is all, of course, a rather complicated system we want to emulate somehow in our numerical and our computer models of the Earth system. So why do we actually need these coupled Earth system models? Well, first of all, given that we have such a complex system like the Earth we're looking at, these models are incredibly useful for understanding processes, interactions, and feedbacks. Because in a model you can manipulate the system, right? In reality, we only have that one Earth, and we, to some degree, doing a large-scale experiment with it by changing its greenhouse gas budget, its land use, and so on. So we're doing that one big experiment, but we cannot do several different experiments at the same time. And this is something we can do with models, of course. So we can play around with the system to better understand what's going on and what kind of effects different drivers, for example, have. We've got lots of observational data. We touched upon this in the first session from weather stations, from satellites, remote sensing data, but they are necessarily incomplete, right? We don't have weather stations in all places of the Earth. In the oceans, we only have, certain ship tracks measured or certain sondes exploring the deep ocean. So we have to do some interpolation between the measurements. And one way of doing is actually, forcing models with these observational data to get a grip what's going on in terms of processes and what data we would measure if we could between the weather stations, for example. And finally, these Earth system models help us to simulate climate states which we cannot directly observe. This applies to Earth's climate history, which is important to understand in itself. But it particularly applies to the future, of course. We cannot measure, how the climate looks like in 2050 or 2100 in a certain place. So we have to rely on models also to inform the decision-making, of course, and this is the topic of this session. So this is essentially one of the main motivations. These are the latest data for the actual measurements of carbon dioxide concentrations in Earth's atmosphere. Worryingly, we do not see any turnaround, right? We know about climate change and its adverse impacts for 30 or 40 years, and nothing has changed in this curve, which is really frustrating to us climate scientists. If we want to look into the future, so how will this evolve in the future, then we of course have to rely on some assumptions how we will behave in the future. These are captured in scenarios, how much we will change, what type of food we will eat, how many of us will be on the planet, how much we will rely on the renewable energies or fossil energies. And these are then captured in these future scenarios, which, lead to different future emissions. And then we feed this into climate models, Earth system models, to see, how the future looks like. And, this is just from the latest IPCC report, projections until the year 2100 for different of these future emission scenarios, showing also some uncertainty due to things we cannot get right in the models. So how do these models work, just in a nutshell, and starting from the atmospheric models, because, you know, this is where climate mostly plays out, although the interactions are important, and also because atmospheric models were the first ones to be developed. Well, they essentially start from the fundamental physical equations of fluid dynamics, right? So this is sort of easy. But we cannot, of course, solve them on a piece of paper. So we need some numerical tools to do that. So we divide the atmosphere into a grid. We discretize these equations and solve them numerically. And that would be easy because, you know, those fundamental equations are precise, but then we have to add what, you know, we call physics into the atmosphere. And this is where it gets messy. You know, radiative transfer is fairly easy. But then there comes clouds and cloud processes are not so well understood and, you know, just difficult to model, as I will come back to in a minute. And then we add, you know, all the other components which we need, and this is how it's happened historically. So we add land surface, oceans, some sort of chemistry, a carbon cycle, biosphere models, ice sheet models, and so on. So our models are getting ever more complex. The resolution increases, and we're eating up all the additional computing power, which, you know, the progress in computer development actually provides to us. So we're trying to get as good as possible and more complex in our models. And one of the things making our life difficult are these interactions, right? And our feedbacks in the system. So feedbacks which can either amplify a perturbation or dampen it down. And these feedbacks are often not really well understood. Just an example for some of these feedbacks, positive feedbacks. One prominent is the ice albedo feedback, you know, when the sea ice is melting, as is shown by this comparison of satellite data from 1979 and 2012. Then, you know, darker ocean gets exposed below the sea ice, and this ocean absorbs more solar radiation, so it actually reinforces the additional warming, right? So this is an important positive feedback, amplifying the warming. But there are also feedbacks not on the physical side, but on the carbon cycle side of things, for example, relating to permafrost. Permafrost is thawing due to the warming and could release, you know, substantial amounts of additional carbon in form of methane, a powerful greenhouse gas, or then CO2. Again, further amplifying the warming effect. And these feedbacks, partly coming from the interactions with the Earth system, within the Earth system, are difficult to capture in models still. So touching a bit back on the theme of the first session, what are some of the challenges we're still facing in these models? And one of the issues I already mentioned are clouds. Clouds are difficult to model. There are, you know, so many different cloud types out there which have different effects on the Earth system. Some warm the climate, some cool the climate, and it all depends on the details. And these clouds are small, and the microphysics and chemistry effects within the clouds are often not very well captured from the empirical side, and thus also difficult to include in the models. And the second thing is actually feedbacks, right? Which lead to our uncertainties in the prediction of how much climate will warm in the future. So the central parameter there is what we call climate sensitivity, which is sort of the global warming for a doubling of the CO2 concentration. And for decades, right, this value has been known to, with some uncertainty, only to 3 plus minus 1.5 degrees. So we know that, you know, any additional carbon emissions will warm the planet, but we just don't know precisely how much, right? And this relates to all these uncertainties in the feedbacks we're still having. And the other thing we're facing is, you know, if we want to project into a warmer future, all our models are tuned and validated for the present day period where we have all the observations, right? There's nothing which tells us that a model which is good for the present day period is actually good for a warmer climate state, right? So this is more of a philosophical issue, but it is a real issue. And one thing we can do is look at past warm states in Earth's history and apply our models there and check, you know, how we are doing. And this is routinely also done in my group at the Potsdam Institute, for example. So to wrap things up, because I can only give you a brief glimpse into what we're doing in terms of Earth system modeling, but as we've seen, this touches upon many of the other disciplines covered in this symposium. The first takeaway message is probably Earth is one of the most fascinating coupled systems, but it's also incredibly complex, right? Which is both a joy for us climate and Earth system scientists, but also sometimes a bit of a frustration because, you know, it's so difficult to understand what's really going on sometimes. But, you know, these coupled Earth system models help us with that. They are fantastic tools. They help us to gain insight into the processes, interactions, and feedbacks. And the present day generation of models are really quite good already, and they're getting better all the time, but some challenges remain, as I explained to you a minute ago. But the most important thing is that doesn't mean that we don't know that there is global warming, of course, right? Because the evidence for past and future warming is not relying on models, but we need these models for future projections and future projections of future climate impacts. And in terms of the decision making, which is the main topic of this session, is that these minor issues with Earth system models are no excuse for inaction. So we really have to move forward and bend down this CO2 curve I've shown you earlier. And I'm looking really forward to further discussions in the remainder of this session. Thank you.